Hello, this is Alex Lamb, and today I'm going to try to provide an intuitive explanation of the variational lower bound while still going through the actual mathematics of the derivation. This subject comes up a lot in machine learning, and in my opinion, the resources that are out there don't give the most intuitive explanation. But if you disagree and you think you know of a better explanation, feel free to leave a comment saying so after you like the video, subscribe to my channel, and cite the professor forcing paper. Later in the video, I'm going to discuss connections between the variational bound and neural networks. There is an idea called the log likelihood trick, which is very widely used in machine learning, including pretty much all neural networks which do classification, which is complementary with the variational bound, both conceptually and in practice. The motivation for the log likelihood trick is that we want to estimate a distribution P, which maximizes the likelihood of our samples from that distribution. If we're doing gradient-based optimization, and we usually are, then we want to be able to compute reasonable estimates of our gradients from a single example or a small subset of the examples. If we assume that the likelihood is independent across all examples in our training set, which is often reasonably close to being correct, for example, in a data set of images or audio files, then we can decompose our likelihood for the data set into a product of the likelihood over all the examples. This is a problem because gradient-based optimization works well when optimizing over sums. For example, stochastic gradient descent that looks at one example at a time has a convergence guarantee if the learning rate shrinks over the course of training. If we instead optimize the log of our loss, we can use a property of the log to exactly rewrite our overall loss as a sum over the log probabilities for all of the individual examples. This allows us to train using stochastic gradient descent, only looking at a subset of the examples on each update. The intuition for why the sum versus product difference is important is that we want to be able to push down our total loss by pushing down the loss for individual examples. If you have a sum of two terms, then pushing down one term always pushes the sum down by that amount. However, if you have a product of two terms, then pushing down one could have a wrong or badly scaled impact on the overall value. For example, if one example has a very low likelihood and the other example has a high likelihood, the impact on the total likelihood of our data comes almost entirely from the example with low likelihood. The log term from the log likelihood has the practical effect of making the loss much larger for examples with very low likelihoods, as you can see in the graph. If you just decided to optimize the sum over probabilities, what would happen is that your model wouldn't care enough about having very low likelihoods on some examples, so it would not learn a calibrated probability distribution. I'm going to provide a quick rundown on the motivation for the variational bound. The basic idea is that it gives us one way of training models with latent variables, which are things in the world that explain our data even though we never actually directly observe them. For example, if you observe that a person is angry with you, it could have many different causes which you cannot directly observe. One reasonable way to try to approach the situation would be to model the different possible things that could have made them angry and which of those things explain their current behavior. Latent variables are one way, but not the only way of introducing structure to your understanding of the world. As was discussed earlier, most machine learning algorithms are built on top of optimizing finite sums, so we prefer models where we can look at a small part of the data and make updates to our parameters that tend to drive down our overall error. The log likelihood trick made this possible for the case where we want to only look at a subset of the examples in our data set. The variational bound makes it possible for us to do updates while only looking at a subset of the possible values of our latent variables. Unlike the log likelihood trick, which allowed us to still push up likelihood, the variational method will force us to push up a lower bound that provides a guarantee on the value of the likelihood. Intuitively, the bound corresponds to the fact that a phenomenon only needs to have a single good explanation. But having your model provide values of latent variables that serve as good explanations for the data is sufficient, but not necessary. It's overkill, but it doesn't necessarily hurt. Using the mathematics of probability, we can rewrite our density p of x as the joint distribution between x and z with a sum over all of the possible values of z, which is called marginalization. Using the chain rule of probability, we can rewrite the joint as the probability of z multiplied by the probability of x given z. This is fairly intuitive. The probability of a given observation depends on how likely it is based on different explanations weighted by how likely those explanatory factors are. Now, if we only had a single example in our data set, we wouldn't need the variational bound, as our objective would already be an expectation over a variable that we can sample from. Since we have multiple examples and we're using the log likelihood trick, the quantity that we're optimizing involves a log of a sum. Later on, we'll be able to prove something specific about what would happen if we simply pretended that the log doesn't exist. But basically, it would encourage the model to try to make the joint over x and z high for lots of different values of z, whereas only a single large value is sufficient for pushing the log out of its region with large negative values. In practice, this corresponds to forcing lots of explanatory variables to explain the data, even if it isn't required for having a good likelihood. This leads us to the actual derivation of the variational lower bound. On the first line, we have an expression for the exact value of the log likelihood for the entire data set. Our next step is to multiply the inner sum by q of z given x divided by q of z given x. So this doesn't change the value, but it sets us up for the next step of the derivation. This proposal q of z given x is a distribution of values of the latent variable which are particular to a specific example x. And at this point, we have no reason to believe that the joint between x and z under q is the same as the joint of x and z under p, our true distribution. So we're referring to q as its own distinct distribution. The next step is to try and create a bound on the likelihood by applying the concavity of the log function. A concave function is a function where if you get a midpoint between 2 points x and y using the weightings alpha and 1 minus alpha, the value at this point is greater than the weighted average of the function at those points. In the variational bound, the function f is the log function, and the weighting alpha is the distribution q of z given x, and the values x or y correspond to the ratio of the joint between x and z under p divided by q of z given x. One interesting consequence is that if q of z given x is equal to p of z given x, the point in the log function that they're weighting over is always the same in terms of z, so the bound is completely tight. There usually isn't a reasonable reason to expect this to happen when optimizing a variational bound, but it's a nice condition to know about. Now that we have this lower bound on the log likelihood of the data, we can rearrange some of the terms to get a new perspective on it. First, we can use the chain rule of probability to rewrite the joint distribution between x and z as p of z multiplied by p of x given z. We can then use the fact that the log of a product is the sum of the logs to decompose our inner term into one term containing the log of p of x given z and another term containing the log of p of z divided by q of z given x. Now there are two really interesting things that we can get out of this. The first is that we have the sum of a sum structure, which allows us to do optimization by sampling a single example and value for the latent variable at a time, and make an update which reduces the overall loss. The second is that the right side term is equal to the KL divergence between q of z given x and p of z. The KL divergence is one measure for how different two probability distributions are, and it has a value of 0 if and only if the two distributions are the same. This has the nice property that, in practice, if we want to push up this bound on our likelihood, we can use any method to make p of z and q of z given x more similar, and not necessarily actually pushing down the KL divergence. The adversarial autoencoder, for example, works off of this premise. One thing that we can do with this bound is set up a specific model where we know that p of x given z, q of z given x, and p of z are well-defined parametric distributions. A very fun example of this is the variational autoencoder. An autoencoder is a neural network which has the same input and output. The idea of a variational autoencoder is that we force a bottleneck in the middle of the autoencoder, which we call q of z given x, to have values which look like they're drawn from a fixed prior distribution, p of z. Then the decoder and reconstruction term of the autoencoder correspond to p of x given z. Now, how do we actually pull the bottleneck of the autoencoder q of z given x towards our prior p of z? What's done with the original variational autoencoder is make both q of z given x and p of z Gaussians with independence across all dimensions. Now the KL term between two Gaussians with independence across dimensions has a simple closed form. We will also have a fixed p of z, so we usually pick a p of z with a mean of 0 and a variance of 1. For that specific p of z, our KL term becomes a penalty which pushes the mean of q of z given x towards 0 and the variance of q of z given x towards 1. So the result of training our variational autoencoder is that we can generate from our model by sampling p of z and using those values in lieu of the encoder's values inside of the bottleneck. Then we run the decoder as usual and get a generated image or some other object. If we really did make the samples from q of z given x marginally similar to p of z, then our samples from the prior p of z should fill the role of the encoder's value well, and we should get reasonable generations assuming our reconstruction penalty is relatively low. Now, in practice, variational autoencoders actually don't produce great-looking samples. They're often quite blurry. However, the model is one of the easiest deep generative models to train, and it's highly stable. Additionally, by inspecting the size of the reconstruction penalty and the KL divergence term, one can get some insight into what the model is doing. In my view, one of the nicest things about variational autoencoders is that they provide a nice formal way of thinking about what autoencoders with bottlenecks are doing and how they are learning the data distribution. So the reason why autoencoders fail, at least the most obvious one to me, is that the bottleneck can't remember precise spatial information, so the model ends up producing a blurry image as its output to sort of hedge its bets about the location of the input object. Perhaps one way to solve this issue is to get rid of the bottleneck, for example, by making q of z given x and p of z more complicated distributions. There's some nice work on this, especially the normalizing flows paper. One simple trick to make variational autoencoders work better is to replace the reconstruction penalty, p of x given z, in the pixel space with a reconstruction penalty in the hidden states of another neural net. For example, a discriminatively trained classifier. This is the discriminative regularization idea from Alex Lamb and his colleagues in 2016. This greatly improves sample quality on the CFAR dataset, as well as celebrity faces, and my understanding is that it is used for the Twitter account Smile Vector, which edits pictures of faces to add smiles to them, so that's pretty cool. Another way of trying to improve variational autoencoders is to use a more complicated model for the decoder p of x given z. To some extent, this is just shifting the problem with the variational autoencoder to another model, but it does mean that the encoder lets us learn an inference model for estimating the value of the latent variable, which could be useful. To wrap things up, the variational bound is a very general way of dealing with the situation where an equation emerges which includes taking the log of a sum. This does come up in the case of maximum likelihood estimation of latent variables, are models with latent variables, but it could come up in other places. Variational autoencoders are one relatively simple way to apply the variational bound to neural networks.